Okay. All right. So here's the review. So let's start off with, we're starting off with dynamics, which means forces. So the dynamics, like we're talking about, we're just talking about forces. Oh wait, shoot, you guys can't see my screen right now. Let me go back. Forgot to share screen. All right, now you should see my screen. Okay, so we got dynamics. So when we think dynamics, thinking of Newton's laws. So the biggest one, what's Newton's second law? Anyone want to chime in with that?
Is it F equals ma?
Yeah, nice. F equals ma. And we have to be a little bit more specific here. Like when we're talking about forces, we're going to put this thing, which means the sum of the forces. All right. If let's say that I want to talk about weight. So weight is the force of gravity. So how do I write weight? Still got our mass. What do I multiply by?
By gravity, no?
Yeah, good job, Luis. By gravity. Okay, so that's our weight. Let's look at normal force one more time. So normal force, we're gonna say that that's F of n, and the normal force is the force of the surface pushing on it. So it's always perpendicular. I'm gonna put that for perpendicular. All right, so let's say these two scenarios. So we got something like this. So here, weight always goes down. So there's my mg, but the normal force is perpendicular. So we got this normal force right here. All right. If it was on a horizontal table, I could just say that mg is and f of n are here. But here, like see how it's perpendicular to the surface. So let me, since we're right here doing this, let me put the mg over here. I'm gonna leave the mg off real quick because we know that that's the weight. And remember, we break things up into components. So I have my component here, and I have my component here. Okay, and this is my angle. Remember, this is the same angle as this guy right here. Okay, so my normal force here, if I'm looking at my normal force, this normal force has to equal this component. So this component is, well, here's my mg, and what trig function am I going to use for the red one if it's touching the angle? Give you a hint. This is the adjacent side.
Sine.
What, Luis?
I was gonna say sine, but
But yeah, since it's the adjacent, it's cosine. Right? So this is the normal force is mg cosine theta. All right, since we're dealing with like inclines, let's look a little bit more at inclines. All right, so here we go. Let's say we have an object going up an incline. This angle. All right, so let's say it starts off with an initial velocity and it's sliding up the incline. And let's say that it's a rough surface. All right, if it's a rough surface, that means it has friction. So we're going to put friction this way. And then let's say sliding up ramp. So sliding up ramp. Okay, we're sliding up the ramp. So we have our weight. So we have mg. Mg is going down. So mg. We have our normal force going up. We'll do that in green. are going, not, I shouldn't say up, it's going perpendicular to the surface. Okay, now here's the common error, and I get this a lot, like this is like the most common error. I have all my forces, and someone will say like, oh, it's sliding up the ramp. So if it's sliding up the ramp, it has to have some kind of force pushing up the ramp. Well, that's not the case. There's no force pushing it up the ramp. It's just the momentum, or it's just sliding up the ramp. It's moving in this direction, but it doesn't have to have a force to be moving in this direction. It had to have a force to start it moving, but it could slide up the ramp and only have these three forces. Okay, so this would be my sliding up. So I could say here, my Fn, my normal force, is equal to mg cosine of theta, right? Because we have this component of it right here. And then my F, well, now we have to, we can have two different things for the F. This thing, is it accelerating? If it's sliding up the ramp, is it accelerating?
Yes. Cause
Yes.
there's friction, no?
Yeah, because there's friction. Yeah, it's slowing down. Its velocity is changing. So yeah, it has a an acceleration. And the acceleration is going in this direction. All right, so if I sum all these up, if I say left is negative, I could put negative f, and then I also have this component of, and I'll do this one in blue, I have this component of the weight. And here, now we have the opposite side. So here's my mg sine of theta. So here I'd have minus mg sine of theta. All right, so I have negative to the left, and it's accelerating to the left. So that means I would have m times negative acceleration.
Wait, Mr. Phillips, I have a question.
Yeah.
How do you know normal force is cosine and the other one is sine?
Okay, here maybe I'll draw like it really big real quick. So we have here, here is our weight, here's our normal force, and here's our friction. All right, so we know that it is, oh, and I should say this, like, sometimes in the AP test, they ask you to draw the forces where they actually act. So friction actually acts down here. So I can move vectors like that. So if I ask like where it actually acts, in that case, it would be like the normal force would be at the surface. This gravitational force would be from the center. So that's kind of tricky. Sometimes they've done that before, but I'll just do it like this for right now. Okay, so Luis says, how do I know what trig function to use? All right, if this is the angle, look, I just made a right triangle here. I made a right triangle. So this component goes down like this. This component goes over like this. Here's my angle. And I use cosine for this one right here because it is the adjacent side. It's touching the angle. So this one right here is mg cosine of theta. This one is opposite. This one's opposite. So this one is mg sine of theta. Does that make sense, Luis?
Yeah, kind of.
Okay. That's kind of tricky, but here I'll actually leave that. So okay. It just takes a little bit getting used to just looking at it, and I mean, if you want to, since we're right before the AP test, you can just memorize that. So f, like in the y direction, is cosine, and then this one is sine.
Wait, would it be because of Takatoa?
Say that again.
Would it be because of SOHCAHTOA?
Yeah.
Like sine with opposite and what's the name? Cosine with adjacent, no?
Yeah, perfect. Nice, man. Perfect. All right, so look at this right here. I have negatives on everything, so I can, and note that my acceleration is going down too, but everything's negative, so I could just make it like this. You just have to pick a direction for it. Okay, that's this is sliding up the ramp. So now let's say we're sliding down. What if we were sliding down? Well, I would do everything the same. Let's make it a little less inclined. I would do everything the same. Except now, what direction is my friction?
Your friction is up, no?
Yeah, it's up.
You're going down.
Yeah. And what is it that actually pulls the object down the ramp?
Gravity.
Gravity. Yeah, nice. So, and technically it's this component of gravity. So really what pulls it down is mg sine of theta. Okay, so I would do the same thing, like I could calculate my Fn. My Fn here is equal to mg cosine theta. And if I did my, now if I'm doing in the x direction, I have, we can say, if we want to say that to the right is positive, I would have a positive F. I would have a negative, this is going that way, mg sine of theta. And that's equal to mass times acceleration. But here the acceleration is going down. So I would have a negative acceleration. All right, let's go on. Let's move on because we got a bunch of stuff to cover. So here, we could talk really quick about, well, let's talk about friction real quick. So friction, I sent you guys out a list of formulas that you should memorize. But friction, the most common one is the kinetic, and that is equal to mu of k times the normal force. And then we have static. Here I need to have a inequality sign. All right, so static and kinetic. Kinetic means moving, static means stationary. And the reason for this, like I can think of one thing, we know that static is always stronger than kinetic, or the coefficient. And this coefficient is always stronger for static. And it looks something like this. Like if we have friction, frictional force, and we have applied force, then we get something that looks like this. All right, so that means that as you push on something, let's say that I have a refrigerator and I'm pushing on the refrigerator. All right, I'm pushing on the refrigerator. Well, if I push at, let's say that it takes 100 newtons for it to start moving. Well, if I push at 15 newtons, it pushes back at 15 newtons, right? So at 15, it's 15. At 20, well, this is really not scale. Let's say at 15, it's 15. And then when I get up to 100, now it starts to move. And once it starts to move, it comes down. It comes down a little bit. So it might take 100 newtons to start it moving, but then only 90 newtons to keep it moving. And then no matter how hard you push, let's say you push at like down here at like 500 newtons. Well, 500 newtons, it has the same friction as it does at like 300 newtons. All right. Again, though, this is the most common one used, like when we're using friction, like anytime something's moving, we get this right here. So that is the frictional force, and it's dependent on the normal force. Okay. All right. So remember that, like this right here, this is a demonstration of Newton's third law, which says that if you push on something, it pushes back on you. And note that these are two forces, but they're on two different objects. You feel one force, the refrigerator feels one force. All right, let's talk about static forces now. So static forces. And we did this before. We did things hanging. And let me ask a question to start us off. Which one of these scenarios, if we call this T1, T2, which one of these scenarios has more, which one is T1 and T2 greater? Which one has a greater tension?
The one on the top, no?
Think the one on top?
Yeah, number one.
Number one?
I'm gonna say number 2 because Luis said number 1.
Yeah. Nice, David. Actually it's number 2. 2 has more tension.
Huh.
Like think about it. Like if you had, like, let's say that this was this had 100 newtons of force pulling down. This one would have both 50 newtons. But as you go like steeper and steeper, now think about it, like it takes a lot more force for these things. Like think about if you're to raise this up, right? Like right here it has it's splitting it, but here it takes a lot of force in order to keep these guys stationary. And now, like, that's just like we haven't proven it yet. So this is how you would do a scenario like this. Like let's say that we have this scenario. I'll do it in black. And then we'll get that one there. Okay, let's give this an angle of let's say that one's phi and this one's theta. All right, so two different angles here. And we got T1 and we have T2. Okay, so now if I do this, if I look at this, I'm going to break this up into the y direction. And in the y direction, I'm going to have gravity going down. So I can say negative mg. And I have to use some trig functions here again. So I'm going to have plus T1. And in the y direction, I only care about this component right here. This component. So see how that's the opposite side? So I would have T1 sine of theta plus T2 sine of theta. And it's static. Normally I would do mass times acceleration. But is this thing accelerating?
Nope.
Nope. So I'd have 0. Okay, that's the y direction. In the x direction, I would have, we have to break this up into components again. So there's my, now I'm dealing with x components. So here I would have, since this one's going to the left, I would have negative T1 cosine of theta plus T2 cosine. Oh, whoops, I forgot, like this T2 here, this is a phi. Just a different angle. Because we could say that these things are different angles. So this would be cosine of phi. All right. Okay, that's a lot on forces. So let's continue and let's just do a quick review.
I just have a question for static.
Yeah.
So does that mean that you have the greatest force is on the less degrees you have, or on the angles?
Yeah, yeah, that's good. So if you said T1 or T2, which one's going to have a greater force? And it's going to be,
T2 because it has the angle is smaller, no?
yep, yeah, perfect.
Okay.
The smaller the angle, the higher the force, the tension. And think about like if you're trying to lift this and two people were pulling on each side, the more and more you pull, the closer you get these two like being like a really small angle, the more force it would take. Okay, let's do a quick one on momentum. So linear momentum. What's the equation for momentum? Something times something. Mass times.
Mass times velocity.
Yeah, good. Mass times velocity. You gotta memorize that. So if you guys don't have that memorized, memorize it right now. All right, so we have momentum. So if we look at collisions, and we did something on this before, we have elastic, which is the bounce, and we have the perfectly inelastic, which is the stick together. And when we think about this, so on this one, momentum is conserved for both of these. Momentum's always conserved, so momentum's conserved for both of these. But this one, only one of them conserves kinetic energy, and that's the elastic. So Ke is conserved, which means that Ke initial is equal to Ke final. All right, so if we had to, like this could become really mathy, like if we had to, like two pendulums coming in together and having an elastic collision, they're going in this direction, and then after they have elastic collision and they're going in that direction. Well, I could have, I could expand this out and say 1/2 mv1 initial squared plus 1/2 mv2 initial squared is equal to, now I have my finals, 1/2 mv1 final squared plus 1/2 m2v2 final squared. All right, seems like a lot of variables here, but it's just saying like, oh, and I'd have to put like that this is mass 1, mass 2, mass 1, mass 2. There's just a lot of variables, but it's really just breaking down that the energy is 1/2 mv squared. So it's only conserved for elastic. But momentum's conserved for both. So conservation of momentum would say momentum initial is equal to momentum final, which if I had two masses, I'd say m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. All right, seems like a lot, but it's just using like these two basic equations. All right, so let's talk about impulse. Impulse is defined as change of momentum. So change of momentum is momentum final minus momentum initial. But I can also say that that is equal to force times time. But we did this the other day, so this is just impulse. You just need to memorize this. And we did this with the scenario. Let's say you have a crash with airbags and a crash without. airbags. Well, in both cases, your change of momentum are equal to each other. Your change of momentums are equal. If you're driving in a car at 60 miles per hour and you hit a tree and come to a stop, well, in both cases, you're traveling at 60 miles per hour and you came to a stop. So your change of momentum is the same. But what's different is the force. Here with an airbag, it's increasing your time to stop, so your force is tiny. Over here, without an airbag, your force is big and your time is small. All right. Any question on that? So you guys good on? I'm going kind of fast because I got some other stuff I want to cover too.
No, actually, it's good.
Okay, cool. All right, so let's go energy now. All right, we already talked about kinetic energy of 1/2 mv squared. And so I can write that Ke is equal to 1/2 mv squared. What's Pe due to gravity equal to?
MGH.
Perfect, mgh. And then I also have one more potential energy, and that's elastic. And that is 1/2 kx squared. And remember K, if I have Hooke's law, says F equals kx. So remember we did this, like if you have a graph of F versus X, the slope of this is your K value, and K is your spring constant. It's how stiff the spring is, stiff or soft. All right, and X, like if you think about what is X, well, X, if we have a spring, let's say that this is the equilibrium position, and then this thing gets stretched out farther. Your X is the distance stretched, or it could be your distance compressed. So it could be like this too. Could be where it's the amount compressed. Okay, so there is that's your PE elastic. So remember conservation of energy. It's your energy initial is equal to your energy final. And you could have different, like it depends on what you have. Like you know, a lot of times the classic one is, you know, something going down a ramp. You start off with a certain height and then you end with a certain speed. So in that case, you start off with mgh and you end with 1/2 mv squared. There's no potential here. And like if you're starting off at v0 is equal to 0, you have no kinetic. So there's an example of conservation. Let's say you had a spring here. So let's say we had a spring that was cockbacked and loaded, and it's gonna go down, you know, a certain distance. Here we would have the energy at the beginning. If it had a certain height, it would be mgh. If it had a potential energy to the spring, it would have 1/2 kx squared, but no kinetic initial. And then final, like if it comes down here, well, let's say at the equilibrium position. At the equilibrium position, if we're going from here to here, it has no spring constant. It still has mgh because it's got another height. Call it mgh2, and then now it has a 1/2 mv squared. So it's all like dependent on the problem. Like I just made these up real quick, but that's like a basic conservation of energy. You take your initial energy and you set it equal to your final energy. All right, so there's we're gonna move on from energy. Oh, well, I guess I should talk really quick about work. Work is force times displacement. And technically it's cosine of theta, because if I have a box and I'm pushing at it at some angle, F at some angle theta. Well, the only actual thing that's pushing it is this adjacent side. So this is the adjacent side, so I need cosine of theta. All right, we also have the work is equal to your change of energy. So let's say I have a scenario where I lift a box a certain height. Well, my work here would be equal to my change of energy. Well, finally, like at the final, it has mgh, and initial was 0. So I could have, in this case, work is equal to mgh. But I could have something like this too. I could have like you're driving in your car and you hit a speed bump or something like that. I think in class, like I said, like, oh, you hit a deer. Just kind of graphic, but let's say you're going here, and here's your V initial. Well, after you hit the speed bump, what happened to your velocity?
Decreases.
Yeah, your velocity now, your velocity final, it decreases. So velocity initial is greater than your velocity final. Well, what happened to that energy? The energy there was work, like the speed bump did work on the car. So here I would say that work is equal to my change of my energy, which would equal to, here I would have, remember change, you do your final first, 1/2 mv final squared, minus 1/2 mv initial squared. And note that since v final is less than this one, your final answer is going to be negative. So if work is negative, energy is lost. All right, so energy is lost in this scenario. Energy is lost to, like, kind of hard to see on this one, but like, there'll be friction, like heat, like things will, what, Luis?
It would turn into sound also.
Yeah, sound, that would be a release of energy too. Yeah, good. And like the speed bump would, have some, it would have some energy, like friction and things like that happening to that. Okay, gonna move on now to, let's go to, since we're talking about springs, let's go to simple harmonic motion. So simple harmonic motion, that's a spring going back and forth or a pendulum going back and forth. That's in simple harmonic motion, or a spring going back and forth, going up and down. That's simple harmonic motion. And we can talk about the period for both of those. For period, we give it a symbol of t. So let's say for a pendulum, the equation is 2 pi square root L over G, which means that if I increase the length here, the period increases. Like, think about it, a really long pendulum is going to have a really long period. If I increase the gravity, like let's say I go to Jupiter, that's going to decrease the pendulum. The pendulum is going to swing really quick, so the period is going to be shorter. So for a spring, the two things that a spring two variables for a spring. Still has the 2 pi. But now it's mass and spring constant. So if you increase the mass, like if I hang a real big heavy mass here, that's going to increase the period. If I increase the spring constant, like if I make it a really thick spring, that's going to decrease the period. It will move up and down really quickly. All right, so a couple other things like that you would have to know for simple harmonic motion. T is equal to 1 over F. And I think we're good for this, just for a quick review. You guys get this one? You good, Luis?
Yeah, we're good.
Yes.
Okay, thanks, David. Okay, let's go circular motion because it's been a little bit since we've seen that. All right, let's say that I have a mass and I'm swinging it around in a circle. And here I have the tension. What direction is my centripetal force going to go?
Counterclockwise.
Yeah, so that I could swing this counterclockwise. So I could say that, you know, like I could say that it's going this way. But what direction does centripetal, like, what direction does the centripetal force always go? Like, centripetal.
It goes to the center.
Yeah, nice. Goes to the center. So, all right. And that means the acceleration goes to the center. So acceleration, the centripetal acceleration is v squared over r. Just something like, just memorize this one, you know, since we're so close to the test. To derive this one's a little complicated. So here's my equation. I can note here, remember that v is equal to r times omega, where omega is our rotational velocity, or angular velocity. So I could say that since I'm squaring this one, so think about if I square v squared, that would be, if I plug in rw, that'd be r squared omega squared over r. Well, one of these r's cancels out. So I could also write my centripetal acceleration as r omega. And r here is the distance from the center. All right, if I want to make this force, if I want to make it a force, well, remember F equals ma. So all I have to do is multiply it by mass. So I could say mv squared over r, or it could be written like this, mr omega. All right, so we did things like a roller coaster going around, and like at the top, what's causing the roller coaster to go in a circle? What's the force? What force causes a roller coaster to like go around this curve and points down?
Would it be centripetal force?
It is. Yep, it's a centripetal force. But remember, centripetal force is due to something. So
Gravity.
Gravity, good. So this is just mg. So Luis, when you're saying centripetal force, mg is the centripetal force. Like, you know, centripetal force can be due to tension. It could be due to weight. It could be due to the normal force. All right. So if I were to draw a free body diagram of this, there's my normal force. And we did it. We kind of said this before. Like, I remember that there's no applied force. A roller coaster does not have an applied force. That's a common misconception. There is no applied force. The roller coaster is just set in motion, and it only has these two forces. All right, so, and then we can say if this thing was moving really fast, around the top, the normal force would be really small and the gravity force would be bigger. So think about like if you're almost like flying off of a track, if you are moving slow, then your F of n, because like think about just on a flat surface, your F of n equals mg. So really slow, your F of n gets closer and closer to mg. This one, you feel like you're flying off the surface, so you feel weightless. So that means like you don't feel any normal force. Okay. Any questions on that? Let's look at gravitational force, or the universal formula for gravitation. Any two objects are going to feel a gravitational force pulling them together. Let's say we're on Earth. Let's give an example of a satellite. So let's say that this is a satellite, and it's going around Earth. Well, we already said that the centripetal, like the thing that's causing the satellite to rotate around Earth is gravity. Might seem kind of weird. But it has an initial velocity, and so the only force acting on this satellite is gravity, and that's causing it to curve around. Like in class this was a long time ago, but we said this was Newton's famous experiment. Like let's say you shot a cannonball this fast, it would hit right here. Well, what happens if you shoot it a little farther? It would hit here. And note that the only thing that's acting on this cannonball is gravity. But let's say you go super fast to where it falls at the same curvature as Earth, then it will just keep going around and it would come right back. And if you're the one who fired it, it would hit you and you would die. So that's the that is why just erase it. That is why a satellite only has gravitational force, and like the gravity is causing it to curve around. So in this case, we have let's say that my F of g. Let's say that we got big G. We have mass of the satellite, and then mass of the Earth. And note, mass of the Earth is really big. And we got my radius squared. The radius would be from the center of Earth, so from here to here, because it acts as gravity acts from like the center of Earth. You can like approximate it as acting from the center of Earth. All right, so here we could say like, oh, well, what this the force of gravity is equal to my mass. Let's say that, all right, this thing's going in circle. This is the centripetal force. So let's say that the centripetal force, where am I going with this? Well, okay, I can just say this. If gravity is the only thing that's acting on it, and you ask like, well, is it accelerating? It is accelerating. Its acceleration is the centripetal acceleration, and this is like the mass of the satellite. So you could plug in here v squared over r. Note that the mass, these cancel out. So here it's just saying that the centripetal force is due to gravity, gravitational force. All right. Last thing, like what time do we got? Let's see real quick. Oh, this has been going on for a while. You guys feeling good for one more thing?
Yeah, no problem.
Okay. Just real quick, because we already went over this, so I'm just gonna write the equations up, and then we'll call it good for today or for our review. And I can post this video because I'm videotaping this right now. All right. Rotational kinematics. This rotational kinematics, you have to memorize these, and they're not hard if you already memorized your regular kinematic equations. Note that I'm just replacing delta x with the delta theta. I'm replacing v's with angular velocities, and I'm replacing a's with acceleration. Oh, whoops, that's all right. There's my rotational kinematics. This is with constant a acceleration. Our most basic equations for we're like, oh, what is my angular velocity? Well, my average angular velocity, that's just delta theta over t. My average angular acceleration is delta omega over t. Think about this. Velocity is distance over time. So angular velocity is delta theta over t. All right, that's just a quick rotational kinematics. And you can note that, let's say you're given a revolution, delta theta, let's say you're given like 1 revolution. Well, a revolution is 2 pi rads around. So you can take, in order to find delta theta, you can just multiply however many revolutions times 2 pi. So if it goes around the circle 4 times, then it's 4 times 2 pi, 8 pi. All right. To go over, let's go over torque one more time. Torque is equal to RF sine of theta, meaning you have something with a, say that's the axis of rotation. Push on it. That is the torque. Maybe you push on it at an angle. That's where the sine of this is where the sine comes in, because really all we care about is this component of it, and that's the opposite side. So RF sine of theta. All right. So torque is also equal to moment of inertia times angular acceleration. This is like F equals ma. Angular momentum is equal to moment of inertia times angular velocity. This is like P equals mv. And kinetic energy is equal to 1/2 I omega squared. All right. These are things you have to know. We had gone over rotational, so I feel like I'm just gonna end it there. Okay, that was a lot, you guys. This was just like a power review session. So, how you feeling?
I feel all right.